Very good. Yes, thanks very much for the introduction, Emad, and yeah, thanks for the invitation to come along and speak. In this session, I'm just going to give mostly a high-level introduction to some solid mechanics, a little bit of historical background. I'm going to talk a little bit about the theory and just end with a very simple built-in example. In the subsequent sessions, the other speakers are going to go into more detail on the actual test case and setups and things like that. So just to start with, I'll just have a slide on my background, just to tell you about who I am. So I did my PhD in 2008 to 2012. So that's when I was first introduced to OpenFOAM. But at the start, I used CFD Online, this online forum, quite a lot to ask stupid questions. But I slowly learned a lot from that. So I found that very helpful. So I'm now a moderator on that forum as well. I'm an editor for this OpenFOAM journal, but also for this Journal of Open Source Software. And then I work on this Solids for Foam toolbox, which I won't speak about so much in this talk, but some of the subsequent speakers will speak about it. So I'm definitely an advocate for open science. Just to start with, the background for OpenFOAM solid mechanics. So many of you, if you're familiar with, let's say, computational solid mechanics, you might use a synonym FEA. So when you say FEA, you really mean computational solid mechanics, even though that's can be any one of number of methods. So in OpenFOAM, it's primarily built on finite volume methods. So finite volume solid mechanics has been around for a long time. It's just much less popular than finite element methods. So some of the first papers came from the early 80s. So there's various different independent groups with different flavors of finite volume method. In OpenFOAM, it's primarily based around the work of this Ismet Demirdzic. Demirdzic was the primary architect for star CD, which you may have heard of, a commercial solver. But the OpenFOAM method is very similar to what they would have used. In the 90s, when OpenFOAM, its predecessor was Foam, so the commercial software Foam, developed by Nabla Limited. So you can actually, on the Wayback Machine, if you search for Wayback Machine, it archives websites from the past, but you can actually find the old Nabla website. And as a consulting company, they offered solid mechanics analysis with OpenFOAM. So you can actually find, if you click on this, I won't do it now. You can find some simple tutorials that they talked about, some large strain, small strain solid mechanics solvers that they had. Then when we got to the early 2000s, when OpenFOAM became OpenFOAM, so when it became open source, 2004, then there's work from various different groups, lots of Viches or Chuts, so lots of Yugoslavian influence, I would say, in this area for various reasons. So there's various different developments on solid mechanics and FSI, and then there's many other independent groups as well. And then particularly in Foam Extend, that's when I got involved, these solid mechanics solvers in Foam Extend. So I would have taken a lot of the work from the group in Dublin and Zagreb and tried to collect it together into various solid mechanics solvers, which you can find in this Foam Extend. And then there were various different independent FSI packages. And even today, you can Google FSI and OpenFOAM. There's lots of different people working on FSI. And then Solids for Foam will be a collection of different methods to kind of generalize them for solid mechanics research and FSI. So that's just the short background. Yeah, so why use OpenFOAM for solid mechanics at all? So OpenFOAM is obviously a very popular open source CFD, primarily CFD software. And so I suspect it's probably the most popular open source CFD software. So lots of people are using it. And many people are familiar with the OpenFOAM format. They understand the structure, the maybe non-conventional structure of the input files in the form of a case. And they understand how the solvers are run and how to use an OpenFOAM case and where results should be and where boundary conditions should be. So if you're familiar with that, then it makes sense if you want to solve other common physics as well. So solid mechanics being one of those things. So maybe you're not looking for the best method, you just want something that you can use in a platform you're familiar with. Added on top of that, naturally, if you're interested in fluid simulations, you probably often will come across FSI or fluid solid interaction problems. So then you have to overcome this challenge of let's say, bridging the gap between different fields and different softwares typically. So one approach is maybe to consider using OpenFOAM to solve the FSI problem all in one place. So that's kind of the first couple of points. Uh, Also for me, just as a research interest, I'm interested in finite volume methods and related methods, just novel computational methods. So there's some curious, interesting features about finite volume methods for solid mechanics. And OpenFOAM is a very nice toolbox or platform for just things like reading in the mesh and developing your own code rather than writing things from scratch or maintaining an in-house code. Just to give you some examples of solid mechanics simulations performed in OpenFOAM. I would have been involved in various projects over the years. I had a number of projects related to metal forming. So this is large elastoplastic strains with frictional contact of crushing a pipe, but also to do with rolling and drawing and different types of plasticity models, etc., etc. So this worked well in OpenFOAM, but these procedures are all developed in a finite volume formulation. You're going to see later on, I think in an hour's time, Ivan is going to give you a talk and go through some tutorials. So Ivan will work on many similar applications. In particular, he worked on these contact procedures, so you can implement these, let's say, quite nonlinear simulations, and the finite volume method seems to work well for at least the cases we were looking at. Towards FSI, and I know there will be talks on FSI as well, and this Sulzer foam has been mentioned. So you may be familiar, if you're from a CFD background, you may be familiar with this dam break case where you have a rigid little block and then a column of water drops and hits it. And then there's an extension of this benchmark case where you have an elastic beam as well. So this sort of problem, this is a multi-phase FSI problem. So you can solve this, for example, in the Sulzer foam, OpenFOAM toolbox. And here's another tutorial from Sulzer foam of a kind of standard simple benchmark of flow over an elastic beam, and this was transient, but there's various different formulations of this benchmark to check your method works. They're solving finite volume solid mechanics in the solid and finite volume fluid mechanics in the fluid, and then it's all coupled all within the same platform. And then this water hammer test case, a pressurized pipe where then you apply a pressure pulse and it travels down the pipe, and even though the fluid is incompressible, so the speed of sound is infinite in the fluid, you actually get a moving pressure wave in the incompressible fluid just because of the finite speed of sound in the elastic wall, basically. So this is often a starting kind of benchmark before you go to kind of, let's say, cardiovascular flows. Just one other one to do with some of the research I'm involved in as well. So let's say continuum style formulations for solid mechanics is definitely one thing of interest, but there's also, let's say, structural formulations. So in this case, these are beams. So these beams are actually fully implemented in OpenFOAM, and they're a finite volume formulation for beams. So these are Simmer-Reisner beams implemented in OpenFOAM, and they're used as mooring constraints in the 623 solver in OpenFOAM. So this is basically an interfoam fluid simulation, and then you have these mooring beams. Yeah, so I said I'm not going to really speak about Sulzer foam, but I just wanted to briefly mention that this Sulzer foam toolbox, which you'll hear a bit more about in the coming talks, is just one of many toolboxes that will add functionality to OpenFOAM. So if you have OpenFOAM installed, you can go to sulzerfoam.com, download Sulzer foam, and then build it, and then it builds on top of OpenFOAM to add extra functionality related to solid mechanics and FSI. For the middle part of the talk, I'm just going to tell you a little bit about the finite volume method, particularly for solid mechanics. And then at the end of the talk, I'll go through an example. So I work with finite element methods as well. So there's more similarities with finite element methods than there are differences, I would say. I'm just going to show this quote from Brian Spalding, which many of you may know. So Brian Spalding was a famous figure in CFD, who sadly passed away just over 10 years ago, or just under 10 years ago. So just to read out this quote, now, however, I recognize the FVM, finite volume method, finite element method dichotomy as being comparable with those between Protestant and Catholic, Sunni and Shia. That is to say, it promotes needless conflict and expense and loss of opportunity. Just to highlight this, that I don't know, naturally in science, people can often be quite very defensive of the methods they use. But I would suggest to try just look at things. This is maybe a different way to formulate a problem, and there's obviously a lot of similarities. And looking at a problem from a different way maybe can help you improve your own methods. So particularly, I look at a lot of finite element formulations and just see how that compares in terms of finite volume. And often there's just different names for the same things, and the ways that work well in both are actually yeah, that works well in one is actually similar to what works well in the other. Yeah, so the finite volume method, you will start with your governing equation. So this is conservation of linear momentum. So this is Newton's second law, essentially, mass by acceleration, equals sum of surface force and volume forces. So you will start with this integral form of the equation. So it's the strong integral form. So in finite element, you will have this weak integral form. You'll have multiplied across by weighting functions, but you don't do that for finite volume, at least in the popular way to derive the finite volume method. And then you apply it to each control volume or cell in your mesh. So immediately one thing that stands out is the finite volume method normally is derived for polyhedra, general polyhedral cells, or convex polyhedra. So this you don't have to derive separate stiffness matrix for squares or triangles. You just apply it to general polyhedra. But when you design a finite volume method, you have to make lots of choices around the solution algorithm, implicit, explicit, or if it's implicit, what type of implicit, how you're going to add stabilization forces. Most of these decisions have to be made for finite element on other methods as well. But I'll just skip through some of the interesting parts, and I guess I'm trying to point out how it's different and similar to like the finite element method or other methods. So if we apply it to this triangular cell here, a couple of things to point out. We have the integration volume. So we're applying this integral equation over this cell itself. And then when we discretize it, we basically will replace this acceleration or stress field in terms of values at certain nodes. And by nodes, I mean where the solution is stored. So in a cell-centered formulation, like in OpenFOAM, we will store the solution at the geometric centers of the cells. So we'll rewrite this equation in terms of displacements at these cells to enforce this equation over that control volume, that volume of integration. But you can also implement vertex-centered methods, and some people do that in OpenFOAM. It's not the standard, so I've worked on that as well. And it's exactly the same idea, except you just store the solutions at the vertices, and then you form integration volumes using this dual mesh. In contrast, finite element, you normally derive it based on the elements, but in effect, you're actually doing a conservation for a center node in terms of an integration volume, which are the adjacent elements. And then the computational stencil in that case is like the boundary. So it'll be the same as a vertex-centered method, but the integration volume is different. Just interesting as well, adjacent control volumes, they overlap in finite element, but they normally don't in finite volume. It's an interesting difference. Finite volume methods and finite element and other numerical methods will all often suffer from numerical instabilities. So you get these zero energy modes. So for example, you might get checkerboarding. This was a large strain plasticity simulation. So when you have this incompressible plasticity, you can often get these pressure oscillations in many formulations for large strains, as we did here. So you have to look at different stabilization techniques, which normally is adding damping or diffusion to the governing equation. So for example, if you use finite element methods, this is called hourglassing. This is one type of stabilization, and similar checkerboarding is a similar phenomenon that happens with finite volume methods, and there's similar stabilization solutions. So OpenFOAM uses something called reach out, but it's kind of hidden the way it uses reach out, or it kind of uses reach out, but it's essentially adding some sort of diffusion that doesn't affect the order of accuracy of the method. But there's other methods like Jensen, Schmidt, Turkel as well. Then another major choice, like in finite element or other methods, is when you solve your equations, you can solve them explicitly or implicitly. So if we do it implicitly, let's say the surface forces are written in terms of the current time unknown displacements, you have to solve some sort of linear system. So here's maybe one kind of key difference with normal, let's say OpenFOAM or finite volume methods and finite element methods. The convention in OpenFOAM due to its history for CFD, is to use these segregated methods. So you take your governing equation and you temporarily decouple it into the x direction, y, and z direction, and then you will solve these smaller, easier to solve linear systems, and you will do many iterations coupling around it. So you can do the same thing in solid mechanics. So that method's not really known in the finite element community. It's not really used. Instead, coupled methods or Newton-Raphson methods are normally used. But if you look at it from that Newton-Raphson perspective, this segregated approach is called like a Picard linearization. So it's essentially a type of quasi-Newton method. So there's definitely similarities you can pose in the same kind of framework. But for example, the same implicit, explicit characteristics you might see in finite element methods, you'll see in finite volume methods as well. So this is just a geometry with a hole over here, and then it's applying like a pressure wave at the side, and you get a wave propagating across. This is the explicit solution, this is the implicit. And then if we plot the is it displacement or stress along a line, you'll have some wave propagating. So the red is an explicit solution for a given mesh and time step. So you get these dispersion errors, these kind of noise errors from an explicit method, whereas an implicit method, you get this diffusion errors, you get smoothing of the solution. And if you have a bigger time step, you get even more smoothing. So all these things are common across numerical methods. Okay. Yeah, so for the last section of the talk, I'll just go through an actual example case. So I'm going to stick to the tutorial that's available in the standard OpenFOAM, as opposed to look at Solves for Foam or other toolboxes, which you'll learn about later. So there's one called plate hole. So a infinite plate with a circular hole is a classic mechanics, solid mechanics test case. So we have there's an analytical solution when the plate is infinite in size, and we can derive exactly what the displacement and the stress solution will be. So often it's used for benchmarking codes or like linear elasticity codes. So in this case, it's obviously not an infinite plate, but it's a plate which is 4 meters by 4 meters with a 0.5 meter radius hole and 10 kilopascals applied on left and right. And due to symmetry, we're just going to model 1/4 of it. So our solution domain will be this top corner with a hole. So how do we run this case in OpenFOAM? So here are the commands. So I'll flick over to the terminal so we can do it as we go. So I guess if you attended the talks this morning, you would have learned a little bit about the structure of OpenFOAM and how to run basic cases. But if you type run, that just is a shortcut to bring you to what's called a run directory in OpenFOAM. And it's just by convention where people store their OpenFOAM models for that particular version of OpenFOAM. You can store them wherever you want. It's just a convention. And then using this foam tutorials environment variable, that's just a shortcut to where the built-in tutorials are in OpenFOAM. And there's a solver called solid displacement foam. Actually, I think this needs to be stress analysis / solid displacement foam. I'll check that. But I'll do that now. And there's one tutorial called plate hole, which is this hole in place test case. So we're just going to copy it to move it there. So I'll just jump across here. I assume you can still see my terminal. So I've loaded OpenFOAM 24.12 here. But this same thing should work on most versions of OpenFOAM. So foam, tutorials, tab, and solids. Is it stress? Yeah, okay. I left out stress analysis. I was meant to put that in. Solid displacement foam, tab, and then plate hole is the only example. So I'm just going to copy that to here into this folder, plate hole, CD inside plate hole. And this is the OpenFOAM case. So you can see here we have, if you attended, I guess, the talks this morning, you learned about this constant folder, system folder, and then zero or a copy of the zero folder. So the structure of the case will look just like the standard OpenFOAM structure. So if you're familiar with OpenFOAM, then there's nothing surprising here. Constant, this is where the mesh will appear. So a poly mesh folder will be created when we run the mesher. But apart from that, its physical properties are stored here. So mechanical properties and thermal properties we can have a good look at. The system folder, then you have your block mesh dict, because it's a simple case. There's a block mesh dict set up to create the mesh. Time step controls, running in parallel controls, and then things to do with the discretization and the solution tolerances. And the single graph is for processing. And the zero.orig, which is just an OpenFOAM convention that sometimes the zero folder is just called .orig, just as a backup. And then when you want to run it, you just make a copy of it to zero. So we have a D field and a T field. So D here represents displacement and T represents temperature. So my background is solid mechanics, so I would always call displacement U. But unfortunately, fluid mechanics people all call velocity U. So OpenFOAM U means velocity, so they call displacement D. So okay, that's fine. There's a block mesh dig set up to make a structured mesh that looks something like this. So we can check this. We can jump over, check it works. So if I ls my case, I just run block mesh. So I guess you maybe learned a bit about block mesh this morning. So it's just reading this input file which describes that block structure and the number of cells, and then running block mesh will create it. And if I parx is just a shortcut I have on my Mac, just to open PowerView on my Mac. That's not a built-in command, so we can just check what the mesh looks like. And yeah, there's our mesh. So just a structured mesh. One question you might have is, oh, well, what kind of meshes can we use? So any mesh that's supported by OpenFOAM, you can use then for the solid mechanics simulations. So I guess of interest, which looks a bit strange if you're from a finite element background, is you can have polyhedral meshes. So you can have meshes where the cells kind of look like little footballs, basically. So creating those, for example, if you use ANSYS Fluent, you have a polyhedral measure. So for example, you can use open source meshes like Gmesh, and that would make tetra meshes, and then there's a built-in command in OpenFOAM to make the dual of that mesh. So it will make the polyhedral version of the tetrahedral mesh. But there's other meshes. You can use commercial meshes as well in importing. Just while I'm here in the terminal, I can open up some of the properties. So we're going to see that. So the mechanical properties. So this test case is for a built-in solver in OpenFOAM called solid displacement foam. So solid displacement foam is a small strain linear elastic solver. So it's limited, although it's a thermal linear elastic solver. So it's the option to do thermal stresses as well. So the way the properties are defined are a little bit limited, but you have a density, Poisson's ratio, Young's modulus, and then if it's running in 2D, then there's a switch basically to flick between plane stress and plane strain. Because OpenFOAM, even for 2D, runs with basically a 3D with one cell thick and special boundary conditions on the front and back. Okay. So then we ran block mesh to create the mesh. The boundary conditions. So 0.orig. We have our D field. So internal field, this is the starting displacement field. This is like the initial conditions. So we just set to 0. And then we have a left, right, down, up, hole, front and back. They were all specified in the measure. And we use different boundary conditions. So there's some symmetry planes. And then apart from that, we have traction free on the hole, traction free on the top, and then applied traction on the right. So this won't match the analytical solution exactly. This is just a finite plate. But you will see here this traction displacement. You can apply a traction here. So 10 kilopascals in the x direction. And the pressure here, this refers to a surface pressure, not to be confused with a hydrostatic pressure. So it's the normal component of the traction on the surface. We saw the mechanical properties. There's also thermal properties, which are not enabled by default, but then control dict, it's just going to start at time 0, run to time 100 and take time steps of 1 second, even though this is a quasi-static problem. And these FE schemes, this grading scheme is the key thing for solid mechanics. So it's basically the parallel for shape functions or interpolation functions in finite element. So rather than continuous shape functions that describe the displacement between the nodes, other methods are used to describe the local linear distribution of the displacement field. So in this case, like a least squares method is used. But also you can specify the time scheme, so it's that the second time derivative set to steady state here. There's also some tolerances, but I'll skip over those. But I will just show you how to run the case. So we're going to run the solver, and then the tutorial is set up to extract the stresses along a line. And then here's a plot that we can run to just plot the stress along a line away from the hole to compare to, in this case, the analytical solution along that line as well. So I'll just do that now. So I'll close this, solid displacement foam. Well, yeah. So in the all run script, it will run a command restore zero directory. That's an OpenFOAM function that all it's doing is just copying that zero orig to zero. And then if we, not solid foam, sorry, muscle memory. So solid displacement foam. So it runs pretty quickly. In this case, the time steps are not really time steps. They're actually using these time steps as iterations. So you end up with a bunch of time steps, but they're actually just outer iterations. I will copy and paste these post-process functions as well. And then I will run this GNU plot script, and this will plot stress along a line. Hopefully if it pops open. Yeah, okay. So this is plotting the stress along a vertical line from the hole here. So if I run this case, displace it, or look to jump to the end time, this is the displacement field. These are the stress fields. This is the von Mises stress. This is the XX stress. I'll just turn on the get power view to create the interpolated fields as well. So I will also change this to be contoured. Very good. So there's our stress concentration. It's being pulled to the right. I can warp this as well. Maybe I'll scale it. Okay, so it's being pulled that way. Very good. It extends the whole, gets shorter in that direction. So we're plotting the stress along a vertical line along the symmetry line. So analytically for an infinite plate, you should have 3 times a stress concentration, a factor of 3 here that drops off. So you can see the analytical solution is the green line, and then the numerical solution are the dots. So it over predicts it, but that makes sense for a finite plate. So if you do a mesh convergence, you'll see it converges to a different answer. But you can match this test case by applying the analytical traction boundary conditions on the boundary. Very good. So we get this. All right, so this is a very short introduction to the test cases, but I'm conscious of the time as well. So this is just to highlight there are some basic linear elastic solid mechanics tools in OpenFOAM, but you'll hear about extensions to more general solid mechanics in the later talks. And there's definitely a growing kind of community-driven ecosystem in OpenFOAM. That's the great thing about OpenFOAM, and that there's a big community of various different solid mechanics, FSI, and related tools. And if you come from a fluid mechanics background, solid mechanics FEM is pretty easy to understand. If you come from an FEA background, you just have to get your head around the kind of fluids way of solving equations or the finite volume approach, but effectively it's very similar. And then, yeah, there's definitely on my own research, I'm interested in various unified solution approaches like for FSI and related methods. Okay, I'll stop that just in the interest of time. I will stop there. And I think the questions will be held in an hour or two's time. At the end of the session, there's a question session. So thanks. Yeah, thanks very much for your time. I'll make these slides available somewhere as well. I guess I can send them to you, Emad.